a week or two.
It'll be good.
Sounds like.
It's kind of weird, but.
Yeah, just what you told them, but yes.
I think that's what we're
You're
gonna
gonna
do.
like, geez, 1 2 weeks. It'll be nice to talk about.
Yeah,
You've been begging for it. Not sure if you'll be able to talk about it.
that's true. I think Clark and I are just different.
But no, I mean, it used to be as a whole job.
That's true.
Okay, I'm gonna finish up on optimization notes today. There was homework on Friday, but I'm gonna check this on Wednesday. So I'll send out a reminder tomorrow afternoon. I'll check the optimization homework. By the end of today, well, by the end of class today, we should be able to get through all the material that we need to preparation for the test. So we're gonna finish up on the day 2 notes on page. Yeah, we're just gonna do some practice, page 11 and 12 in your packet, and then Wednesday we'll switch over to the test review packet, which we just picked up today. I'll have help sessions in the morning. Wednesday, Thursday, Friday, I'll send out Teams link as well as I'll be recording them. In terms of the afternoon, I'll be available in the afternoon for Wednesday, but fine for Thursday. So I'll be available morning help sessions in the afternoon. Wednesday. If you want to come by, I can definitely help if you have any questions. Okay. And then during the help sessions, I'll just pick out problems from the review packet that that I'm not going to get a chance to do in class, but they're just going to be repeated types of problems that we're already going to do in class. Okay, so just going to pick out some additional problems for if you feel like you need that additional practice. But in the packet, it has all the keys. In addition to all the problems for you to work through. Okay, so I encourage you guys to start looking through it via time today and tomorrow, and then I'll kind of give you a little bit of a head start in terms of preparing for Friday test. Okay, so if we can turn to page 10, let me just kind of give a bit of a recap. As far as optimization. So with optimization, we always want to start off reading the problem and looking to see if we can figure out a primary equation. The way you know what your primary equation is, you want to look for those key words like maximum, minimum, least, greatest, optimal. Whatever those words are describing is going to be what you're going to be identifying as your primary equation. So here it says maximum area. So you know that area is your is ultimately what you're trying to find the derivative for. And you're going to create for this problem, we created our area equation. But then once you create your area equation, you're always going to have to look to see, okay, is there a second variable that's sticking out on the right side? If there is, that means we need a secondary equation to provide some support so we can get this primary equation down to one variable. Yes.
I need the packet.
Okay, sure. Okay, so here for this problem, the secondary equation is coming from perimeter because there's 200 feet of fencing, so that's indicating that, well, that's talking about the perimeter around this this region here, this rectangular region. So then we went ahead and we built our perimeter equation. We solved for one variable. It didn't matter which variable, but I like to, between x and y, if they're equal, then I'm going to try to get my way down to terms of x. So I solved for y, made my substitutions, and I got my area equation down to one variable. Now, once you get your area equation or whatever your primary equation is down to one variable, you should be able to rely on just power rule. Okay, so we're not going to have to, with optimization, at least on this test, we're not gonna deal with any messy derivative rules, okay? So no messy quotient or chain or product rule. Really, we should just be able to rely on power rule, but it does require some cleanup here. I mean, we could go through, a combination of product, chain, and quotient, but there's no need to, right? Especially if everything can be cleaned up nicely. So then, what we can do here is we can distribute that 2x through just in the numerator. We get 400x minus 8x squared all over 3. We can always split up into individual fractions, especially if the denominator only has one numeric value. And then we get it down to this 400 over 3x minus 8/3 x squared. That's sitting as a nice equation for us to work with, for us to find the derivative. Easy power rule there. So we go ahead and we find the derivative using power rule. And as soon as you find the derivative with optimization, you're always going to do the same thing. You're always going to set your derivative equal to 0, because that is where we find our optimal solution. Okay, whenever our derivative or our slope is 0. So, and also we don't do different steps for maximizing or minimizing or least or greatest. It's always the same thing. We always find the derivative, set equal to 0, and solve for x. So we solve for x there. I got 25 feet. Now, whenever you solve for x, you're basically at the end of the problem, but the only thing you have to do is make sure you go back and you reread the problem, make sure that you're providing what they're asking for. Here they're asking for dimensions. So we have x, we need to find y as well. So we go back and search for an equation that we can use for y, and we have one here. So plug 25 in for x, solve for y, and that is your other dimension, x and y. Okay. I think we got close to finishing, but it's the same steps, very similar steps as what we did with the previous problem. Okay. Any questions so far? Optimization. So today we're going to just do more practice with this. The only thing is that we're going to be involving or bringing in cost, because we want to use a cost to optimize area, or we're going to try to minimize cost given some dimensions. Okay. So let's go to page 11. Okay, let's read the problem there, number 1. Okay, a rectangular field is to be fenced off along the bank of a river. No fence is required along the river. Okay. If the material for the fence costs $8 per running foot for the 2 ends and $12 per foot for the side parallel to the river, find the dimensions of the field of largest possible area that can be enclosed with $3,600 worth of fencing. So, okay, let me put this problem on a separate page so I can have enough room here. So we have a rectangular field. We're only needing fencing on 3 sides, not along the side that has that's directly next to the river. So let's say we had the river here, and I have 3 sides of my rectangular fence. All right, what are we trying to optimize here? Area, right? We see the word largest, right? That's describing area. So we know that star next to area. I'll go ahead and label these sides here. I'll call the horizontal X. I'll call the vertical Y. So what's the area here? This XY. Now we also have perimeter going on here. So perimeter, okay, is adding up all the 3 sides here. So I have X plus 2Y. But it doesn't give us something that is in terms of the perimeter, right? It gives us something in terms of cost. So cost is going to be related to the perimeter. And the reason why is because, the amount of fencing is directly related to how much money you're going to be spending, right? Because you're not spending money on the space that's created inside this the rectangular shape. You're spending money on the outer regions that's created by perimeter. So you can put a cost under this perimeter because we're starting off with perimeter, where we're going to eventually kind of use this information to transform it into a cost equation. Okay. So we have cost that is associated with each of the sides. Okay, so the side that's parallel to the river is $12. So I'll put a parentheses there, $12. Then the ones that are running on both ends there, it's a little cheaper, $8. So we're basically going to be involving cost into our perimeter here. So I'm going to basically just multiply. Oops, sorry, my bad, the other way around. Right, so multiply the cost into the amount of fencing that we need. And then that's going to basically translate to our cost equation. Okay, so what is that going to come out to be? 12 times x, so 12x plus what? 16y, okay. And we know what cost it is, right? We know this is going to be $3,600, so we can go ahead and make that substitution. Okay, does it matter which variable we solve for? In this case, right, either one would get you to the answer, no issues. So I'm going to just target y because I just would rather work in terms of x. So, but you can obviously go a different direction and you'll get the same answer. Okay. Okay, so we have a perfect substitution in for y. So we know we're putting this into the primary equation, right? Because ultimately, you're trying to find support for your primary equation. Put a star next to it because that's what we're ultimately going to be working on, cleaning up, find the derivative, right? Everything's going to come from that area formula. Okay, from here on out, it should be pretty straightforward. Clean it, distribute the x through, split up into individual fractions, separate into, right? Once you separate, get each term set up and ready for power rule, then find the derivative, set equal to 0, and solve for x. Okay. Use your calculator. I think with optimization, it's the setup, right? The setup is what's going to feel different, but then once you have it, once you have your primary equation down to one variable, it should just feel like a relatively easy process, especially if you know that you're not dealing with any complicated rules here. You're only dealing with the power rule, but it does require you to take the time to clean up and separate those terms into individual fractions. Okay. And then once you solve for x, go back, read the problem, and see what else you need to find so that you can present your answer fully. All right, so try that. I'll be right back. Okay, so once you distribute the x through, 3600x minus 12x squared all over 16. Split them into individual fractions. Clean up each individual fraction. 3600 divided by 16 is 225. Reduce the second fraction. And then find your derivative. 225x becomes 225. 3/4x squared becomes 3/4 times 2x, which is 6/4. Say your derivative equal to 0, solve for x. Okay, 3/2 x equals 225. Divide both sides by 3/2. Same thing as multiply by 2/3. X equals 150. Right, so we have one of the values of our fence, one of the sides. Go back and read the problem. It's asking for dimensions. So that means we're looking for y as well. So y is going to be 112.5 because we found an equation for y and we used plug 150 in for x, get it down to 112.5. Okay, any questions? Okay, let's look at number 2. Okay, number 2, rectangular storage container with an open top is to have volume of 10 cubic meters. The length of this base is twice its length. Material for the base costs $10 per square meters. Material for the sides is $6 per square meters. Find the cost of material for the cheapest container. So, okay, so we're looking for trying to optimize cost, right? So trying to optimize cost. Okay, let's see if we can draw this diagram here. Okay, so I have the base being one length, and then on the other side of the base is going to be double that length, so x and 2x. The problem doesn't provide any information about the height, so I know there's not going to be a relation in terms of x, so I got to find another variable. You can use h or y. I'll choose h for height, but any variable is fine. Okay, so we're trying to optimize cost. Now, cost is going to come from the material that's being used, right? And the material that's creating this box is with surface area. So there's a hint. We're minimizing surface area. The reason that the cost is not associated with the volume, because volume is the space inside the box, right? We're not paying money for what's inside the box. We're paying money for what's creating the box itself. So we know the cost is going to be associated with the surface area and not with the volume. So let's put a star next to surface area. Because ultimately, we're going to transform this into the cost equation. But let's talk about surface area first, and then we can work in the cost and eventually call it the cost equation. Okay, so surface area, again, it's just the area of the surfaces, right? So how many surfaces do we have for this problem here? 5, because they're telling us it's an open top. Now, if they say it's a closed top, then that means we need to pay money for that, for the top side as well. So then, but here, we only need to worry about the 5 sides, okay, the base and the 4 vertical sides. Okay, so let's build the area of each of the surfaces. Let's start with the bottom here. What's the area of that bottom, that base? Okay, 2x squared. Okay, we have 4 more sides to worry about. Okay, let's talk about the front facing side here. What's the area of this surface here? 2xh, okay. Is there another 2xh? The back, right? The back is also 2xh, okay? So we'll add that in. What about the vertical sides? What's the area of this? xh, okay. And is there another xh on the other side, right? Okay. So we should have we should be accountable for 5 sides. Okay, so 1, 2, 3, 4, 5. You got the base at the bottom of the box, and you have the 4 vertical sides. Okay. Now the cost. Okay, we're going to transform this into the cost equation. But to do that, we have to find out how much we should be, how much each of the material is going to be costing, right? So, so it's the length of, let's see, the material for the base costs $10 per square meters. So we know that this base is associated with $10. A material for the sides costs $6 per square meter. So we know that all of these sides, right, $6 per square meters. So now to find the cost equation, we just multiply the cost into the surface area for the appropriate sides, and then we're going to add them all up. Okay. So the first one here, this gives us what? 20x squared, and then multiply and add. Now you could have easily done this. You could have added all the like terms first and then multiply the 6 through. Maybe that's faster. But right now, I just want to kind of prove to you that every area, every surface has its own cost associated with it. Okay, a bunch of like terms that we can combine. Okay, 24 plus 12, that's 36. All right, so we're trying to optimize cost, right? I put a star next to surface area, but eventually it turned into a cost equation. So we look at the right side. We know we want to find the derivative, but there's that h, right, that's sticking out, right? So we need a secondary equation to help us out. What's our secondary equation? Volume, right? That's the support, right? The volume is the support that's going to help us get this cleaned up. So what is the volume of this box here? Length times width times height, right? So 2x squared h. We have the volume that's given to us, so 10 is equal to 2x squared h. Looks like h is going to be the easiest variable to replace over here, right? There's only one h here, so if I get that replaced in terms of x, then I'm ready for cleaning up and power rule. Okay, so divide both sides by 2x squared. Solve for h. All right, what does this reduce to be here? 5 over x squared, right? The 10 and 2 reduces, stays up in the numerator, but the x squared stays in the denominator. We got a perfect substitution here. Okay, so see if you guys can finish the problem from here, right? So once you make that substitution, get each term cleaned up and ready for power rule. And then from here, same steps as before, right? Derivative set equal to 0, solve for x. solve for x, you're basically at the end of the problem, but you still need to go back and read the problem and see, okay, do I need to plug x into something else to present what they are looking for in the problem? Okay, so my cost equation, place h with 5 over x squared, do some cleanup. But I still need to, once I reduce that second set of x's, there's still that x in the denominator. Prefer not to go through quotient rule, especially if I don't have to. I'll bring that x up to the top, make it 180 x to the negative 1. Then I can find the derivative using power rule. Find c prime, set c prime equal to 0, and then solve for x. 40x equals 180 over x squared, cross multiply. 5 by 40, take a cube root of both sides. So x comes out to be around 1.65 meters. Okay. So given the restriction of the volume of the box has to be 10 cubic meters, and given the restrictions of the cost of each of the surfaces, we know we're trying to optimize. We know that with x 1.65 meters, our cost was going to be at its most optimal. Okay, so then we go back to the problem because we have x, but maybe that's not what it's asking for. What's the problem asking for? Surface area. 2. Yeah, find the cost of the material for the cheapest container. Find the cost. So basically, we just have to be able to find the cost given this x value, right? So do we have a cost equation we can use? Yeah, we have a bunch of them, right? So you can choose any one of them, or you can just choose the one that you feel is the easiest to plug your x into. And I think this is the easiest one without, having to deal with h and without having to deal with the negative exponent. But really, any of the cost equations work. So again, insert 1.65 into x, because once you solve for x, then you're just trying to figure out what to plug in terms of what you're looking. So you shouldn't have to deal with the derivatives anymore once you get down to that. So given this volume restriction and the cost of each of the surfaces of the material, our optimal cost is going to be $163.54 when our when the base length is 1.65 meters. Okay, if we can turn the page, we're gonna try on page 12, numbers 5 and 7, and then we'll circle back to 6 just to have you guys do some more practice. But let's talk about number 5. Okay, so the setup is very unique for these types of problems, but then once you see the setup, it's going to be the same for all of these here. So it says Highway 400, average 54,000 cars per day for its first 5 years of charging 50 cents per car. Scientific research concludes that for every 5-cent increase in the toll, the number of cars will be reduced by 500. In order to maximize revenue, what toll should this highway charge? So let's think about the scenario here. We know that, obviously, if you keep increasing the toll amount, then technically your revenue should increase, right? Because you're charging more per car that's coming through the toll road. But the reality also is that if you keep increasing the cost, then eventually cars are going to try to find other ways to their destination, right? They're going to try to avoid that toll, especially if it's to the point where they don't think it's worth it. So here's what their study concluded is that each time they raise the cost, that's true that they are getting more per car, but then they're going to be losing 500 cars on average each time they raise the toll. So we're basically using this data to try to figure out what is the optimal amount that they can charge on the toll and still maximize their revenue, right? Because it's going to come to a point where if they keep increasing the cost, eventually you're going to start losing, the revenue is not going to be maximized. So just trying to find that balancing point. Okay, so here's the formula that I'm going to have you guys write down here. The revenue is equal to the change in the toll amount multiplied by the change in the number of cars. Total revenue that they're bringing in is the toll amount, basically it's total amount times number of cars, right? However much they're charging per car, multiplied by how many cars are coming through. But then there's this game that we have to play in setting this up. Okay, so we'll call this R of X for representing revenue. Now the change in toll amounts, okay, let's talk about this here. How much is toll going to start off as? 50 cents, all right, so 0.50. And then for each increase in toll, we'll let the variable X represent each increase in the toll amount. So each time they increase, the toll amount is going to be by how much? By 5 cents, right? So plus 0.05 X, okay? And we'll let X represent each toll increase that they announce. Okay, multiply by the change in cars. How many cars do we have to begin with? Okay, 54,000. But each time they announce a toll increase or they put a toll increase into effect, what's going to happen? Minus 500. Okay, so I want to kind of have us see this this equation in action here. So that means, if we raise by 5 cents, we're going to lose 500 cars, right? If you raise it by 10 cents, you'll lose 1,000 cars, right? So you're going to see this balancing that's going to come. Okay, any questions with the setup? Okay, so that's really the hard part. The hard part is just get to this point. After this, you're just cleaning this up, distributing, expanding, getting ready for power rule, find the derivative, solve for X. Okay, and here we don't need a secondary equation because everything is in terms of X, right? There's no secondary variable on the right side. So, the setup Takes a little bit of time to get used to, but then once you can get that down, then everything feels pretty straightforward. Okay, so go ahead and try that. Use your calculator, see if you can expand, distribute all your terms through. Because, I mean, I guess you could go through product rule if you really wanted to. F prime G plus F G prime, but, you know, for me, if I can avoid product and chain and quotient rule and just rely on power rule, that's my preference. But yes, you could technically go through the product rule and the same answer. Okay, so after I distributed everything through, I just rearranged my terms, x squared first. You don't have to do this, but I just rearranged the terms, combine my terms. I got it nice and clean. Everything is ready for power rule. Find the derivative, set equal to 0, solve for x. Okay, so x equals 49. So what does that mean? Context of this problem, what does that 49 mean? Yeah, so on the 49th toll increase, they're going to be able to maximize their revenue because it comes down to the point where they've raised the price enough, and they have just enough cars where they can maximize revenue. Because after this point, they're still going to be bringing in money, but it's not going to be as good, right? Because at this that tipping point, right, that 50th one is going to cause the number of cars to be low enough where they're not pulling enough. The amount that they're charging per car is not worth it. So they want to stop at that 49th toll increase. Okay, so now let's go back to the problem here. Let's reread that to see what they're asking for. In order to maximize revenue, what toll should this highway charge? So how can I find what toll amounts? And then plus that to 50, right? So, okay, so we just basically insert this 49 into the expression that's going to give us how much they're going to be charging. Yeah, $2.95. Okay. Hey.
Yeah.
Now, if the problem is asking for how many cars are there going to be at this optimal rate increase, then you would plug 49 into the x for this expression. If they're asking for, what is the revenue that they can bring in at this optimal rate increase, then you would plug 49 into both expressions and then solve for find that revenue amount. So again, once you solve for x, you're pretty much done. You just have to kind of figure out where to insert into whatever part of the equation is to get the necessary information that answers the question. All right, so I would like for us to practice another one of these problems because it does feel kind of new. So if we can skip a problem down to number 7, and you're gonna set up the same way here, except, your revenue is now gonna be, the change in, the change in, the rooms rented multiplied by, the change in, amounts per rental room. Okay, so go ahead and read number 7. With these problems, it's always going to be one expression that's going to be increasing and the other one that's going to be decreasing. So here, each time they upcharge their room, they're going to have less customers, right? Because they start looking at other alternatives for resorts, hotel, especially if the cost continues to rise. But their goal here is to try to find that optimal amount, that optimal uptick in room charge so that they can maximize their revenue. Okay, now what feels a little bit off about this X value here? Yeah, well, technically, the way that they've defined it, we can't have half a rate charge, right? And also, yeah, we can't have half a room. But yeah, each rate increase is a full rate increase by $5. It's not there should be a half. But the idea is that this is technically where the optimal result is going to be. So we know that as they keep increasing the cost, their revenue is going to continue rising, but it's going to come to a point where it's going to start dipping, right? And that optimal rate increase is when x equals 12.5. But we can't quite get to 12.5 because of the restriction of whole numbers. So what's our next best option? Either 12 or 13. And then we can just test which one is the better one, right? Is the revenue going to be better at 12 or is it going to be better at 13? So we can plug 12 and 13 back into the original revenue equation, right? There's a bunch of them that we can use, just not into R prime. Now, if you plug into either any one of those, you're going to realize that both 12 and 13 is symmetrical here. So both 12 and 13 is going to give you close to optimal amounts, right? We can't get to 12.5, but we can do 12 and 13. Which one is better? It doesn't matter because they both are going to give you the same revenue amount. And then finally, they're asking, based off of this, what's going to be the number of rooms at this situation, at this 12th rate increase, and what's the price of the rate? So I just chose to plug in 12, but you could also plug 13 in and get a different series of numbers, and that's fine as well. That's what happens here. If you can't quite get to your optimal, then you can just get close to it by using the closest whole number. Okay, I encourage you guys to start looking through your test review. Your homework for Wednesday is the optimization homework, which I will send out a reminder tomorrow. Okay, but if you get a head start with test review, that'll be good. I'll add another day for you to review Wednesday and Thursday in class. Also, morning review Wednesday, Thursday, and Friday. Okay, don't forget your phones. It's not guaranteed. That's why I went and I tested it to see which one gave the better revenue.
Because I was hearing early this part. You know.
So here, I kind of have to do a little bit of test, though, because I knew that here my optimal solution was absolutely not. Here, my optimal solution is 12.5. But 12.5 doesn't quite fit into our restriction. We need to be able to do a rate increase by 7 numbers, not by the decimal. So if 12.5 is not the best, then maybe either 12 or 13 supposed to be. So I need to figure out 12 or 13 calculated original revenue equation, because I want to know which one offers the better revenue. Well, I know that 12.5 is the best. So the closest numbers is 12 and 13. I know I'm choosing between 12 and 13, but I don't know which one it is. So I plug 12 and 13 back into the original revenue equation to see which one gives me a better. And they're both good, both the same, so it doesn't really matter. Thank you. Have a great. See you guys Wednesday. I want to take a higher one. Because you're trying to make money for the hotel, so you want the higher one. Have a good day. See you Wednesday.
Right.
Well, wait for